Well, hi everybody. Welcome to Mathematical Systems number 4. And what we're going to talk about today is something called clock arithmetic. And then we're going to actually try and show that it's a group. And given that, we're going to introduce a new operation called A mod n, where a is some integer and mod n will be an integer, and so we'll introduce that notation as representative of clock arithmetic. So what you can see here is I have a clock, and so we're going to use this clock to illustrate clock arithmetic. And just so you know, in general, clocks always run clockwise, so they kind of have this rotation, and in general they're broken up into 12 5-minute segments, which you can see by me drawing that angle right there. Now, given those things, we can use this to make a set, and then we're going to describe clock addition. So what would the set be? Set would be 0, 1, 2, 3, ... up to 10, 11. Now why doesn't it include 12? Because 12 is actually 0 when you're counting. You get back to the beginning. So for instance, when we say 12 noon, in some sense we mean it's 0 o'clock. That's our starting point. Or when we say 12 midnight, it's our starting point. And so if we have 2 hours plus 5 hours, we know that that's 7 o'clock. 2 hours plus 5 hours is going to be 7 o'clock. And if we have 5 hours plus 10 hours, we know that that's going to be 5 hours plus 10 hours, 2, 4, 6, 8, 10, and we're going to end up at 3 o'clock. So I'm going to move this picture. Oh, it's not letting me pause. So here we are, and we're looking at another clock I have at my house. And once again, here's our set A, and we're going to define the binary operation as addition as you would on a clock. So in other words, if you added 5 o'clock, 10 hours past 5 o'clock, and you end up at 3 o'clock, that's what we're doing. In reality, this addition is really add two numbers, divide by 12, and then record the remainder. And so this is very much like we have seen before in an earlier problem where I described this for you. So add the two numbers, divide by 12, record the remainder. So if we're at 5 o'clock and we want 10 hours past 5, 5 plus 10 is equal to 15. And then we take 15 divided by 12, which is 1, remainder 3, and then we record the 3. And if we do this in that pattern, then what we get here is we get this addition table. This is in your book on page 760 if you want to follow along. And with this addition table, we now have described the arithmetic of the clock using the 12 divisions every 5 minutes. We of course could have divided the clock into 60 minutes, one for every minute, and that would have given us 0 through 59, and we would have had a different kind of clock arithmetic. But this is where we start first of all. So now the question becomes, is this a group? And so what we want to know is, do we have a group? And so we've seen these kinds of tables before. This is very familiar to us. And so the question is, does it have closure? And the answer is yes, because all the elements in this table are elements in the set. So we know it has closure, and we would actually say that. We would actually write that out. Number 2, does it have the associative property? Well, is it associative? And the answer is, well, certainly it has to be associative. You could do an example like 5 plus 3 plus 6 equals 5 plus 3 plus 6 using the binary operation we've defined. And you're going to end up in the same place. You're going to end up at 2. 5 plus 3 hours is 8, plus 6 more hours is at 2 o'clock, a.m. or p.m., depending upon where you started. So you can see that it works for one. Question is, will it work for all of them? And the answer is this kind of arithmetic is associative, therefore it will be associative for the clock arithmetic. Finally, is there an identity? In other words, one number that gives you 0 for everything. And if you look right here, you see all the zeros there. Excuse me, let me undo that. I apologize. Well, now it's undid the wrong thing. And what you'll see here is that the commutative property also holds. A plus B equals B plus A. Why? Because if you take that diagonal line all the way up and down, you're going to have a mirror image of the elements where they add together. So let me see if I can show you what that is. So here's what it is. My picture is actually wrong. Let me draw it again. When checking for the mirror image, you draw the diagonal this way. And when you draw the diagonal corner to corner this way, what you'll see is that the numbers here match the numbers here, and these numbers match these numbers, and it does it all the way to the corner. And they'll match, so you know that if I had like 4 and 8, and I had a number here, that if I had 8 and 4 and a number here, they're going to be equal distances across the diagonal, and those two numbers are going to match. And that's why it's commutative. So what we really have is not only is clock arithmetic a group, but it's actually a commutative group, which is kind of nice. So I'm going to talk about modular systems, which is the end of section 13.2. And what we're going to do is we're going to introduce a topic called congruence modulo M. It's a new definition where I write A is congruent to B in mod M arithmetic. So what's this mod M arithmetic? Well, it's what we've been doing on a number of examples since the last time. It's where we take A divided by M and then record the remainder. Alright, so what we're doing is comparing remainders after division. So we can know if two numbers are equal. There are a couple of ways to say this. A divided by M, then the remainder is B, or A and B have the same remainder when divided by M. For example, and this one becomes really helpful. For example, in mod 12, which is clock arithmetic, if I take 10, alright, mod 12, is that going to be equal to 22 mod 12? Or, excuse me, just 22. Actually, excuse me, I wrote it backwards. What if I said 10, is that congruent to 22 mod 12? That's how you write it. You have the bigger number here, and then the one that's the remainder is written there. So why does that make sense? Well, mod 12 means I divide 22 by 12, which is equal to 1 with a remainder of 10. So this is equal to the remainder right here. And so that's one way to say it. I could say it the other way. I could say 22 has a remainder of 10 when I divide by mod 12. So this would be like the arithmetic problem, and then this would be telling me what the remainder is. So it's an interesting thing, but it's a nice little arithmetic, and we'll look at a couple of examples. So the first problems you have are problems like this, and they're asking you, is this true or false? Alright, so does 41 have a remainder of 6 under mod 7? Well, how would I figure out? I'd take 41 divided by 7, and that's equal to 5 with a remainder of 6. So the reality is 41 is congruent to 6 in mod 7 arithmetic because it has a remainder of 6. Alright, let's pick one that's not true. How about 23? Is it congruent to 2 mod 4? Alright, so if I take 23 and divide it by 4, I end up with a quotient of 5 and a remainder of 3. So is my remainder equal to 2, which is the remainder, what it's supposed to be? The answer is it's not. So while this one was true, this one was false. And now you know why, so make sure you don't just answer true or false, but you show why when you do this. Now the next thing you want to do is you want to be able to add things together. So what if I had 3 plus 4 mod 8? Alright, what's that equal to? Well, that's equal to 7 mod 8. Okay, well, but what if I had 5 plus 6 mod 8? Well, that's going to be equal to 11 mod 8, which I know is the remainder upon division, so it's equal to 3 mod 8. And fairly simple problems at that point. Okay? Now, you can do this with multiplication as well, and it will lead to a couple other types of problems. So that's it for the video. I hope you enjoy it.